I'm going to introduce James first. He's a mathematical communicator based in the Southwest, and you can usually find him on Baidu 5 talking about current affairs under mathematical lens. And he also gives talks all over the UK on a range of mathematical subjects, from mathematical web development all the way to prime number theory, which is going to be the topic of this talk. And his main interests are usually in fun little bits of pure math, but you have an idea for a topic, he can create it as well. James?
Brilliant. Thank you very much. Hello, everybody. I'm James. As Rosa said, I'm a mathematical communicator. I like talking about maths in all subjects. I don't care. It's maths. I love it. You'll get to know that over the next coming hour. Basically, how this is going to work is I'm going to talk for half an hour. We're going to have a 5-minute break, and I'm going to talk for half an hour again. I also suggest you have a piece of paper handy, because I may ask you to do things as we go along, or you may want to note things down for later interest, that sort of thing. So we're going to start off kind of pretty simple. I've been told that you've done primes kind of, but we'll start from the beginning anyway, just to make sure everybody's on the same ground, because I don't know whether you're all mathematicians or any of your groundings are. So if I share my screen, or rather content from a second camera, and I'm going to press that one. Oops, are you going to behave? Are you going to behave? Probably not, because that one, if I stop share, no, it's misbehaving. This is brilliant. There we are, now you can see me in the big screen. Right, so if I go to that one, not the visualizer, and we go to my slides. Here's some slides that I have prepared. I like slides. Slides are fun. So let's get going. Who on earth am I? As you've probably already been introduced, but I like maths. I'm actually a student, but I do way too much with my time. I'm a web developer. I do research into generalized trigonometry, which is another one of my talks. If you want to have me back, I can come talk about generalized trigonometry and dynamical systems. That stuff stuff I do is to do with water and sloshing problems and stuff like that. I also talk on Radio 5 about current affairs. So I'm a regular on there. I go on and I talk about what's going on in the world, just with some maths, lots of maths. So recently I've been talking about kind of decision mathematics and talking about minimum pass and stuff like that. And also writing a book. But let's move on to the maths, because you're probably not interested in who on earth I am. Firstly, I'm going to put a few notes here, because we're all mathematicians. We like completeness. And unless I say otherwise, I'm focusing on positive numbers. So depending on your definition of the naturals, or natural subscript 1. So the natural starting at 1. So 1, 2, 3, 4. And no, I saw it tonight here, but today isn't my proof of Goldbach's conjecture. That's next year. Join me on the 31st of February. And if you do have any questions, please put them in the chat, mathematical or not. I'd be happy to run through some proofs at the end, if people are interested, or just kind of any general questions. So I'll try and leave some time at the end to just talk about stuff. And I've got these slides the wrong way around, and I forgot that. Before we disappear down the rabbit hole, let's talk a bit about patterns. Patterns may or may not exist. So some things just don't have regularities. Some examples of this would be in chaos theory. Go look that up if you're interested. A pattern can be described as a universal law, i.e. a formula, or it can just exist, okay? And the more complex the pattern, the more mathematically bogged down the rule becomes. So when we're describing stuff like water, we have to use vector calculus and all these nablas and differentials and operators and all these funny things just to describe water. But because it's so complex and the pattern's so complex, we have to use all those funny symbols. So as the talk goes on and we get into more and more complex patterns, the mathematics will get more and more complex. Until at the end of the talk, we're talking about the Riemann hypothesis, and we're doing advanced, complex sum things. And all we were talking about in the beginning was numbers that only have two factors, one of themselves. So this brings me to section 1. What are the primes? I'm going to move through this section pretty quickly because of your education and what you're doing. I think you probably know a lot of this stuff already, and I don't want to waste your time. So primes, what are they? They're lonely numbers, really. They have two friends, one and themselves, but you can't really be friends with yourself, so you actually have one. And so if we look at the numbers, we can kind of bring out a list of primes. So 2's a prime, 3's a prime, 5's a prime, 11's a prime, and so on. They're all primes. But how many primes are there? We can do a simple bit of maths or a simple argument that proves or shows us that there are infinite primes. So if I told you they're infinite, you'd probably have to believe me. You probably do believe me because you know this fact is true. And how you do this is basically you can take some subset of numbers, prime numbers. Let's take 3 primes, so 2, 3, and 5. And we can multiply these primes together to get 30. Now we can add 1 to the sum, and we've got a new prime number. So we've assumed that there are 3 primes, but we've proved that there are 4. So by proof by contradiction, there are infinite primes. Yes, I'm aware there's a more general way to do this, but forgive me, there are infinite primes, and that's the proof. Next, 1. Is 1 a prime? Is 1 not a prime? You probably already have your idea of what a prime is, and you probably already know or have an idea of whether 1 is prime or not. And we can go back to our definition that we started off the talk with, and we can ask, does it have a friend? Its friend would be 1, which is itself. But also, the definition of prime is as 2 friends, 1 and itself. So it actually only has 1 friend, but you can't be friends with yourself, so it has no friends. So no, we don't call 1 a prime. We call it a unit, but that won't concern us. We just need to know that 1 isn't a prime. Now, we're probably going to go on to some stuff that as undergraduate mathematicians or postgraduate mathematicians, we feel a bit more comfortable with. We know that all this stuff that we've done exists. It's a bit boring. This stuff is a little less boring. And if you haven't seen it before, it's quite interesting. So if I give you a number, if I get any number, I can tell you if it's prime. But the question is, how do I do this? If someone gave me 37, I say, that's not prime. There's 2 ways. First is long and convoluted, and we can divide our number by every prime between 1 and the square root of that number. Or if you're going to be pedantic about it, between 1 and the floor of the square root. So if the number isn't divisible by all those primes, the number itself is prime. Take an example, because I'm not good with words. So let's take 37. Square root of 37 is approximately 6, because square root of 36 is 6, and 37 is greater than 36. And 37 isn't divisible by 2, 3, and 5. How we know this is that 37 isn't even, and we can do the digit sum of 37, which is 3 plus 7, which is 10. And we know that if the digit sum of a number is divisible by 3, then the number itself is divisible by 3. So 37 is 3 plus 7, which is 10. 10 is not divisible by 3, hence 37 isn't divisible by 3. And knowing whether 37 is divisible by 5 is pretty easy. It's only divisible by 5, it ends in a 0 or a 5, which 37 doesn't. And 2, 3, and 5 are the only primes less than 6. So we've checked all the primes between 1 and the square root of 37, which is 6. So 37 is prime. Did I say? I may have said 37 isn't prime earlier. I meant 37 is prime. Scary slide alert. Please be aware that throughout the talk, there will be these slides where I think the mathematics gets a bit more in depth. These may not worry you if you're, as your undergraduate and postgraduate mathematicians, but if there's anybody here that isn't mathematicians, these slides may be the time to disengage your brain if you really don't like maths. But if you really don't like maths, what on earth are you doing here at one of my talks? Or even in a maths society? Come on, you all like maths. So please don't disengage your brain. Use your brain. It's fun. So if you've done any sort of recreational maths, or you've kind of thought about maths in any great detail, you've probably come across factorials. They come up in probability and statistics, or even like little number puzzles. I remember someone sent me a number puzzle once, and it was to use 4s to come up with every number between 1 and 10. So 1 would be 4 divided by 4. 2 would be 4 divided by 4. 2 would be, I can't remember, 4 of the square root of 4 or something. And you just use only 4s to come up with numbers between 1 and 10. And for one of the numbers, you have to use a factorial. I believe it was 8. Yeah, it was 8 or something. Or was it 7? I can't remember. You could do it somehow. And you had to use a factorial of one of them, or that was the easiest way. Otherwise, you had a load of 4s going all over the place. I just made it very much easier. And that was the first time I come across this. But I've got slightly sidetracked now. Factorial is like a shorthand for doing a very simple operation. So we notate it with an exclamation mark. And if we take the number 5, we can say that 5 factorial, 5 exclamation mark, or 5 bang, is 5 times 4 times 3 times 2 times 1, which is 120. So the way you do it is you just take the number, times it by 1 less than that number, and then times by 2 less than the number, times 3 less than the number. You can see the pattern on the screen. You just do that for any number. That's what a factorial is. It's not that hard. Now we talk about something that's probably new, unless you did some weird and wonderful further maths modules. And if you did weird and wonderful further maths modules, I approve of you very greatly, because yeah, they're the ones I did. And we learn about something called remainders when we are in primary school. We learn that 5 divided by 3 remainder 2, or 7 divided by 4 has remainder 3. And we don't ever see them again, which at the time I thought was a bit weird. During my mathematical education, at some point I looked back and thought, whatever happened to remainders? Probably a lot of people do. And the answer is, here, this is where remainders went. And we don't see it again because the mathematics surrounding them is decently complex, but at the same time, incredibly useful. So we can notate it with the bracket after the number we're remaindering, with the divisor after the word mod. So 5 mod 3 would mean the same as the remainder if we divide 5 by 3. Or 7 mod 3 is 7, the remainder when 7 is divided by 3. So on. And so the example here is 2. There's some nice number theory stuff. If you study number theory, this will be very familiar to you because it's the first thing you do in any number theory course. And yeah, primes use this quite a lot. We're not going to use it that much. We're just going to see it pop up here and there. And here comes the scary bit. It's something called, I think it's Wilson's theorem, yes. It says that P is prime if the remainder of the factorial of P minus 1 divided by P is P minus 1. So there's some nice notation, and we'll come back to that in a minute. If we just take the example of P being 5, we want to find out if 5 is prime. So let's take P minus 1 factorial, which is 4 factorial, which is 24. And we can divide 24 by 5, which we know is slightly less than 5. And we can, in fact, we can write it as 24 on 5 is 20 on 5 plus 4 plus 5, 4 over 5, sorry, which tells us the remainder is 4. And 4 is 5 minus 1, so 5 is a prime. Look at the notation. That's what it says. If P minus 1 factorial, which is P minus 1 times P minus 2 times P minus 3 times all the way down, is the same as or congruent to, which is that symbol there, P minus 1 mod P. So the remainder of P minus 1 factorial divided by P minus 1 is, oh, sorry, P minus 1 divided by P is P minus 1. Yeah, that's all that was. It wasn't actually that complicated. So we got through that decently quickly. So we can move on to more interesting stuff, probably stuff maybe you haven't seen before. So we can talk about the Sieve of Eratosthenes, Quadratics, Green Tau Theorem, the truth about prime formulae, and GIMP. So come on. Oh, computer, come on. There we are, good computer. Right, first, the Sieve of Eratosthenes. On your screen, you should now see some little squares on the left. So you've got a green one here, which has a 2 on it, a green one that has a 3 on it, a blue one that has a 4 on it, and a blue one that has a 5 on it. The blue one's numbers aren't very easy to spot, but they're there. And the holes in them, a certain fact about the real numbers. You can split a real number into 2 categories. Either it's prime or it's composite. If a number is composite, you can write it as the multiplication of some prime numbers. So we know that 6 is 2 times 3, and 9 is 3 times 3. In fact, this kind of factorization is unique for every number. So only 6 is 3 times 2. And if we take these pieces of plastic and we put them on top of each other, they do a thing. And this thing is why it's called a sieve. So you can put them on top of each other. If you took that 2 and the 3 and you put them on top of each other, you would only see holes through the numbers that were divisible by 2, which are the holes on the 2, and divisible by 3, which are the holes in the 3. So you'd have stuff like 6, 12, other numbers. And if you add the 4, then you'd have 2, 3. Oh, sorry. I'm getting myself mixed up. I'm doing it the wrong way around. You have the numbers. If you put the 2 on top of the 3, you'd have stuff that isn't divisible by 2 and isn't divisible by 3. So it'd be stuff like 1, and then there would be 2, and then 5 and 7, which we know is the primes. And there'd be stuff that isn't primes, but isn't 2 and 3. So stuff like probably 49. Then you add the 4, and that does the same. So it'd be 1, 2, or 1. Yeah, 1's there because it's a slight difference. And you'd have numbers that are primes once you stack them up, basically. And this sieve is from Greek times. It was a huge step forward from trial division, which was our first test for primes. And for a small set number, say 25, as we have here, this is the most efficient way to find primes. So if you have numbers, small numbers, and you want to find how many numbers between 25, you just take away all the 2 divisible by 2s, take away all the divisible by 3s, take away the divisible by 4s, and take away all the divisible by 5s, and then you end up with all the primes. Well, you'd have to go up to 7 as well, because 7 is a prime, then 11, but still. This was amazing, right? It was Greek times, though. So we hope that we've moved forward with Sieves since Greek times, and we have, but only recently. You have more efficient sieves nowadays, and well, nowadays was 2003 when the sieve vacuum was born. The sieve relied heavily on the fact that 60 is a number with many factors. So in particular, you have 2, 3, and 5. They are factors of 60, and they're also primes. So you could say that if a number is divisible by 60, then it's divisible by 2, 3, or 5, or a mixture of both. And that helped a lot, because instead of doing 3 calculations, you're doing 1. So that cut down on computation time a lot. Then you can mark off the squares of the primes, and you can check that a number is square-free. A square-free number is a number that isn't divisible by a square. So we can take something like, finding a square-free number is hard. Let's think about 13. That's a square-free number. That's also a prime. Maybe, no, basically 9. 9 is definitely not a square-free number, because 9 is divisible by 3 squared, which is itself. Basically, it's numbers that aren't divisible by 4, 9, 16, 25, 36, 49, and so on. Oh, I've got them written here. 22 and 30. They are square-free numbers. If I read my slides. Right. That was sieve vacuum. Then we can move on to quadratics of primal nature. And I think at this point, this is where your piece of paper comes in handy. I'm going to ask you to do a couple of things. So if you're going to take a number, make it a small number, please, because otherwise it's not going to hurt me, it's going to hurt you and your brain and mental arithmetic, okay? You're going to have to do some mental arithmetic with it. And take any number less than 40 and do this to it. Square it first. So on your piece of paper, take your number, square it. So times by itself. And now you've done that, we can subtract our original number. So if you've got a calculator, this will be useful. If you haven't, well, just do it in your head. It can't be that bad. I'm sure us mathematicians can actually do mental arithmetic, because I know I can't. And third one, if it's going to behave, slides, please behave. Add 41, I think it's our final one. So you've taken a number, you've squared it, you've subtracted your original number, and you've added 41. Now, maybe you've got a rather big number, maybe you've got a small one, but I can promise you this, it's greater than 41, and it's prime. If you're querying whether your number is prime, go back to the slides, well, go back a few slides and just take, well, subtract 1 for it, do the factorial, which is also going to be a pain in the arse, and divide it by p. Then it should be 1 less than the number. I can promise that. Reason for that is also, this is nice, this is a spiral, and all those blue dots, they're primes. It's a spiral of Euler, I believe. And that's another version of it. I just thought they were pretty. All your numbers are primes. If you've got any problem, put it in the chat and I'll tell you why your number didn't work. And because we're all mathematicians here, we all knew what we were really doing. I wasn't fooling you. this talk is kind of for people that aren't mathematicians as well, but we all knew what we were doing. We were plugging a number into this quadratic. The question is, why does that work? Well, if you do a bit of algebra and you I think it's a minus some b, a minus 6, I think the substitution is, and then you square it, and then you fiddle with the algebra for a bit, you end up with something under mod 6 is plus or minus 1. And because of the twin prime conjecture, which is a different thing that we don't touch today, but it's a thing, maybe we should go into my, tell you what we do. We're going to move over to here, visualizer. So we have numbers. Why this works is basically you have some, call it alpha. We're going to call it a minus 6. So a minus 6. I think that's the substitution. And then we can say plug alpha a minus 6 squared minus a minus 6 plus 41. And then doing the algebra here, you end up with some quadratic equation, which is beta n squared plus gamma n plus nu is, well, it's not 0. But I'm not going to, these are just Greek letters. I'm not going to do the algebra for you because it's long and tedious. Well, it's not that long. It's just a bit tedious, and I don't really like algebra. And then we can take beta n squared plus gamma n plus nu mod 6, which is our remainder we talked about earlier. And you can then just take a 6 out of this, and this beta and gamma are naturals, or they're whole numbers basically. And then you've got a nu over 6 times nu, and times 6, and then you end up with it being equivalent to plus minus 1. That may have been slightly confusing, but basically put in a substitution, fiddle with the algebra, do a bit of number theory, it's plus or minus 1, hence it's always prime. And because of twin prime conjecture says that, well, I think it's twin prime conjecture. I will be shouted at if not. It's that every prime can be, I think every prime can be put as 6n plus or minus 1. And that's a pattern in the primes. We don't talk about it here. But yeah, it's just about primes and plus or minus 1 and 6. 6 is a magic number. Right, let's move back to the slides. If you have any questions, please put them in the chat. It's there. It's there. No, wait, there we are. It's down there, somewhere down there, I think. And you may have been wondering what that funny equation on my slides is. Basically, this equation at the bottom here with lots of numbers, it's a very long number. This is another prime generating polynomial, and I think it produces it up to 21, if I'm not mistaken. And it may not be as good as our quadratic. The quadratic was found by Euler, but it's only a binomial. It's only a binomial. So it's very good for a binomial when we don't have that square term, because the square term allows a lot of freedom in the equation. If you've only got a linear term, there isn't very much flexibility there, and it's a bit like it's very non-stretchy. I'm sure you saw that in linear algebra. Slide alerts! I do like that penguin. That penguin's very cute. And let's talk about green Tau theorem. Again, something that you may or may not have come across. Here, the top picture is of Terence Tau. He's a very famous mathematician. Well, Ben Green is also a very famous mathematician on the bottom. I actually met Ben Green. I met him at IMO, which was all very good fun. He was absolutely bats, as you would expect. And there's Terence Tau. Never met him. Ben Green told me he was a good person. They're two people. They come up with this theorem, and we're very much briefing over this because this is going to blow your brains out. It did for me, but I find it honestly interesting. We can find a function of the form, a linear function, a plus bn, where a and b are just numbers. And this proves a prime for all n. Again, it's just a binomial, and we've got to note that this is a existence theorem. So it doesn't actually prove what we want to find, but it's useful. Technically, it says that we can find a function that produces k prime outputs, where k is any number of our choosing. So I just choose k to be sufficiently large, so we get all of the primes. So k is infinity, really, but people stop noticing after a good 1,000. So we can just put it somewhere over there, somewhere, big number, and we get all of the primes. As I said, unfortunately, that doesn't exactly solve our problem. We have a pattern, but the pattern is an existence theorem. We have a theorem saying it exists, not that we can grab this formula and find all the primes. If I had in front of me about 3 books of numbers that you can just add as coefficients to this equation, being a and b, yes, then I would be sitting here saying, yeah, we have a rule for the primes. But unfortunately, that's not going to happen because those numbers are going to be very, 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 very large, and way too large for anything that we are going to be able to tangibly deal with. So we have to look at other areas of mathematics. We have to go deeper into the mathematical rabbit hole. And yeah, we have to keep searching. So we know there must exist a formula. However infallibly insane that is, we still have to worry about where it is. So you may now be asking, how do we find these big primes? Well, the answer to that is GIMP, which is the great internet Mersenne prime search, or GIMPs, if you're going to say that. But I think GIMP sounds a bit nicer. Well, people from all over the world are basically using their computers to check possible Mersenne primes. They're using something called cloud computing and joint computing, and basically people link up their computers through the internet and they do primes. So they're looking for primes of the form 2 to the n minus 1. And what we have our quick 5-minute break. A little question. How many digits does the how many digits does the largest Mersenne prime have? Someone's putting in the chat that there are, yeah, 2, I think it's 2, 4. That sounds about right. But have a look, is that right? GIMP, 24 million. Yeah, you got it on the T. It's 24 million. 24? Yeah, 24,862 and 48 digits. Yeah, that's what the Mersenne prime is. Right, let's get on with the second bit. We've had a couple of questions in the chat, but I will deal with that at the end. So back to 3. Yeah. Someone mentioned this. Yes. Oh, break time. I screwed that slide. Yeah. The biggest Mersenne prime is 2 to the 82,589,993 -1, which, as mentioned, has 24,862 and 48 digits. And this is Mersenne prime 51. So we've only got 51 Mersenne primes. And as you can see, there's a nice linear relation between the, so linear, to do with the date and the exponent. So that's nice. I just thought it was quite nice there's a linear relation between the two things. You're a statistician, that makes like you. Yeah, it is 500,000 digits larger than Mersenne 50. So they're getting pretty big, and they're getting bigger each time, as expected. So we're going to look at a couple of patterns in applications, and before we rest our heads and kind of appease the the applied mathematicians, before we dive into the pure depth of Riemann hypothesis, which is probably what a lot of you here are here for, because that's the most famous thing. So, cicadas, come on, let's have a listen. If you've ever heard of cicadas before, you're probably wincing at this point. Oh, no, behave. There we are. That's painful. Yeah, I hate that noise. It's awful. They're noisy biters. And like primes, which is very amusing. Again, if you've probably done any mathematical reading, you've come across these. They are very, very kind of big when you talk about mathematical communication and sort of, they're a good topic to show primes. You may have already heard of them, especially if you're from Australia, New Zealand, or the US. They hatch and come out of hibernation every 17 or 13 years. And they can't jump. They've got lovely colours on them. They just make an awful noise. They're very interesting. The reason for 17 or 13 is one species comes out every 17 and another comes out every 13. I find it very amusing that one species does one prime and another species does the other. And yeah. Also, interestingly enough, I forgot what I was going to say. Yeah, their noise, they use the primes because they come out of primes number of years because of the regularity. So there's a certain irregularity. That's a brilliant word. I can't really say that one very well. And the cicadas use it to their advantage, and that's why they come out every 17 or 13 years to kind of evade predators. Also, now polygons and petitions. This is my favorite part of the talk because I'm also a geometer. I do way too much. I just like maths. Maths is fun. And we all know we can construct polygons with a compass and straight edge. It's what the Greeks did. It's very much a form of early geometry, and we all know about it. But it may be a surprise to you to know that you can only construct a regular polygon if the divisors of the edges are Fermat primes. Fermat primes are 2 to the 2k plus 1. Note the stacked power of 2. And so we can plug in 0 and we can get 3. And we can plug in 1 and we can get 5. And yeah, so we can only construct a regular polygon if the number of sides is divisible by a Fermat prime. So you can take 5 is divisible by 5, which is itself. So it can be constructed with a straight edge and a pencil. And same with a triangle, because 3 and hexagon, because 6 divided by 3 is, well, it divides 3. And a decagon, that's one, James. A decagon, which is 10-sided, and you can divide 10 by 5, same with 12, which is a dodecagon, and so on. You can just start constructing if you really want to. Also, any polygon can be made with a compass and a straight edge and an angled trisector if the number of sides it has is divided by 2, 3, or a Pierpont prime. So a Pierpont prime is something of 2 to the n times 3 to the m plus 1, i.e. 7 is a Pierpont prime as 7 is 2 to the 1 times 3 to the 1 plus 1. Or we can have n and n to be different. So 2 to the 2, which is 4, times 3 to the 1, which is 12, plus 1, which is 13. So you can construct a 42-sided shape as 7 times 3 times 2. Unfortunately, I'm not planning on doing that this afternoon. I'm not constructing a 42-sided shape for you. That is left as an exercise for yourselves, if you so want to do so. Work out how to do it. Have fun. And finally, you can split a convex polygon for any normal polygon. It's like a square or a triangle into portions. But the size need not be a power of a prime. So like 2 squared, but not 6 squared. It gets cooler. These portions are also able to be equal size. So if you take a square, I'm going to go, there we are. A square, if I do that, visualizer, come on visualizer, I'm going to draw a square, a wonky square, because I'm not very good at drawing things. And a square has 4 sides. 4 is 2 times or 2 squared. And we can do this if and only if there is a square in there. So we have there's a square, and that square is a prime. So 4 is 2 squared, but 6 is 6 squared is 3 squared times 2 squared, which isn't exactly a square, so we can't do it. Okay, so if I move back to my slides, 3. Don't see any more. Okay, that's all about geometry. That was kind of, I quite like those facts. I find them quite interesting. I think they're like nice little tidbits. Primes, more primes. We like primes. Primes are used extensively in cryptography, which is what makes the technical world safe. Mainly because of the fact we don't know if there's a good pattern for them. So when you buy something online, what keeps your details safe, what keeps credit card details safe and stops hackers stealing it and spending all your money is the fact that primes are incredibly hard to factorize. One of the most well-known uses is a Diffie-Hellman exchange, which if you're a computer scientist, you will know off by heart. So let's explore how primes are used in this using 2 characters, Alice and Bob. Get your brains in gear. This may be slightly confusing. So Diffie-Hellman is used to exchange 2 secrets between people without explicitly telling the other person your secret. It's like a guessing game, but less about guessing, but more without modular arithmetic. Ready? Let's play. Scary slide alerts! Diffie-Hellman. So we have Alice and Bob, our 2 characters. They agree publicly, so both of them know, that they're going to use a modulus, which is 23, and a base 5, which is a primitive root of modulo 23, which is something we don't have to worry about. It basically means that 5 times 23 mod some other number is 1, I believe. Back to my number theory classes. So Alice is going to choose a secret integer, 4. She then sends Bob big A, sorry, which we're going to call G, which is our base, the base to the power of her number she's chosen, secret number, modulo P. So we've got G, which is 5 to the 4, modulo 23, which when we calculate that, so that's 5 to the power of 4, divided by 23, and then take the remainder, which is 4. Then, I remember this slide. Sorry, I'm just remembering something. It's that. Right, let me move my webcam. We're going to go down here. There we are. We're going to move down here for a bit. And Alice chooses a secret integer. Now you've seen this bit. And then she's going to calculate big A, which is g to the A mod P. And then Bob's going to do the same. And he calls his secret integer B, little b. And then he sends Alice big B, which is g to the little b mod P, which is 5 cubed mod 23, which when you calculate it is 10. So you do 5 to the 3, divided by 23, take the remainder, is 10. Now, Alice computes little s, which is big A big B, sorry, to the A mod P, which plug in numbers is 10 to the 4 mod 23. Calculating that, we get 18. And this is where the magic happens. Bob computes also little s, which is big A to the little b mod P, which is 4 cubed mod 23, which is also 18. So what's happened here is the fact that 5 is a primitive root of 23, which means we can do this g to the a mod P, and then we can take that number and do b, big B, which is g to the b, and take that to the power of a mod P. Basically, what you end up with is the fact that we probably should complete this. Yeah, Alice and Bob now share a secret, which is the number 18. So if we go to here, as mathematicians, we know quite readily that a plus b is b plus a. This is called commutativity of multiplication. You may not know that fancy word, but that's the fancy word for it. So we also know that if we have g to the a to the power of b, that's equal to g to the ab, because you multiply the numbers, which then by commutativity of multiplication is g to the ba, which is g to the b to the power of a, which is what we've done in our cryptography example, basically. And then those two numbers, which is little s, well, little s, take the mod 23, yeah, which is the same as little s. That's fine. So you didn't see that, but yeah, we have, go back to that one. We have g to the a to the b, and g to the b to the a, which is this. Take them both mod 23 as they're the same number, they'll be little s. That's fine. That's not that hard to understand. Right. So we can now move on to the next slide. That's what Diffie-Hellman is. It's basically a way to share secrets, but it uses primes and uses the fact that you can do g to the, basically the fact that you can use commutative addition with powers of numbers mod a number. And that's, again, look up primitive root modulos or modulo primitive roots, and you'll get some more information about why this works. We won't go on that today because we can move on to the Riemann zeta. I don't know how much time I've got left. I don't know if any of you have to leave exactly at 3 o'clock. This is kind of taking a bit longer than I thought it would, but we're going to, please stop me if I need to stop. But if you don't have to go, I'd quite like to talk about Riemann zeta functions. If you've got a question and you don't want, if you've got a question and you have to go, please put your email in the chat and I'll get back to you with your question, because this is me just running over. I don't know how long it's going to take, but I'll try and make this as quickly as possible because I know this is why most of you came to this talk. So, Riemann zeta functions. Basically, one of the most famous mathematical problems is the Riemann hypothesis. And there's a related zeta function, which is this, which is the first function on the slides you can see, which is zeta of s is the sum from 1 to infinity of 1 over n to the s. And we can write that a different way. And basically, we're going to look at how we can write this a different way because it's quite a nice proof. Basically, we can write it as the product where p is a prime of 1 over p, 1 over 1 minus p to the negative s. We can do some hand-wavy mathematics and say that basically it's about finding patterns in the primes, hand-wavy mathematics, and this harmonic series is -112. That's basically, if you've ever heard of 1 plus a, or 1 plus a half plus third plus quarter plus fifth plus sixth plus seventh, and so on, it's -112. According to Riemann zeta functions. Don't ask. There's some other funny definitions that we won't go into today that produce a -112 for infinity, which is fun. This is Riemann zeta functions. Right. So we've got the Euler product formula. To prove this Euler product formula, which is the second formula here on this slide, we can do something quite pretty, and I thought this was quite pretty. basically, first thing you do is you take the Riemann zeta function and expand it, as we've got there. And we're going to do something which is a bit like our sieve of Aristoteles. And we're going to times it by 1 over 2 to the s. So then we get all the even terms. And what we're going to do now is we're going to subtract these two. So you get, when you subtract them, that cancels with that. That cancels with that. That cancels with that. So you get rid of all the even terms and base down to 1. So we'll see this in the next slide. There. So now we've got 1 minus, we've got 1 minus 1 over 2 to the s zeta s, which is just subtracting the 2 and pulling out zeta s, which is just a function. And now we've got all the odd terms. We can do the same thing with 1 over 3 to the s, which will remove all of the numbers divisible by 3, which will remove 3, 9, probably 15, and so on. And you get rid of all the numbers divisible by 3. Then you do it for 5. Then you do it for 7. Then you do it for 11. Just following the same procedure, and we'll get something like we had earlier with the sieve of Aristoteles. You get a sieve that removes all of the numbers, and we do it for all the primes as well. So on the right hand side, we'll only have 1. So on the left hand side, we'll have 1 minus 1 over 2 to the s, 1 minus 1 over 3 to the s, 1 minus 1 over 5 to the s, 1 over 1 minus 7 to the s, which is all the primes. And then we divide it and do a bit of jigging, and we get the zeta of s is equal to this, which if we rewrite this slightly, so the visualizer, we have that if we have something of 1 over 1 minus 1 over p to the s, which is our general term where p is a prime, we can then say that's equal to 1 over 1 minus p to the negative s through just some fiddling with the exponents, which is then the same thing as what we had in the previous slide. So if we take the product, which is what pi means, and p is prime, 1 over 1 minus p to the negative s, that's equal to 1 over 1 minus 2 to the negative s, 1 over 1 minus 3 to the negative s, or 1 over 1 minus 5 to the negative s, and so on. So we just proved they're the same thing, and this is where this formula comes from. It was originally found by Euler, but Euler found a lot of things. So let's move on to prime number theory. Let's define a new function. We're going to define a function pi of n, and its number of primes less than n. So pi of 3 is 2, because, well, I think it's actually 1. I made a slight error in the slide, must have been a typo. I was writing these quickly. So pi of 3 is 1, because the only primes less than 3 are 2. And pi of 10 is 4, because you've got 2, 3, 5, and then 7. They're all primes less than 10. And we can plot this function, and it'll be very important to us. Right. Here's a function. You see, it looks a bit curvy. And I've already ruined this because I've already talked about this, but you couldn't see it. And we're going to try and bound this function. And we can use prime number theory, which states that the limit as x goes to infinity of pi of x over x line x is 1. And yep, that's our limit, and that's what prime number theory says. Because we divide them and the limit as x goes to infinity is 1, they approximate. When x gets very, very large, pi of x is equal to x over line x, or approximately equal. So what we found is a lower bound for this prime counting function. A lot of my research, as I've said, is in finding lower bounds for functions or bounds of functions that are just a bit odd. So let's try and find a upper bound, which we've already seen, which is the logarithmic integral, which is the integral from 2 to x of 1 over line t dt. And this is an upper bound, as you can see. Look at this picture. This is the bit you missed last time. You have the a bit like a root function, but a bit kind of like up here, and then a logarithmic integral, which is that. It's a better bound basically because it's closer. And what's this mean? Why should we be interested? Again, I've already said this. Basically, the prime number theory states in some ways the denseness of the primes, and primes are as dense as x over line x, or x is approximately line x. There's nothing to do with me. That's fine. Oops. There we are. Right, I've missed that. I've gone away from the side there. And right now, Riemann hypothesis. Back to this. The interesting bit. You're probably here listening to me ramble about primes. And Riemann hypothesis states that the non-trivial zeros of the Riemann zeta function has real parts of a half. So the a of a plus bi is a half for all the non-trivial zeros of the zeta function. The trivial zeros are the negative integers and 1, I believe. And we can relate these to primes using some complex mathematics. So we can define we can define another function, j of x, which is pi of x plus half pi root x plus a third pi cube root of x plus 1 over n nth root of x. And note this function is an infinite. It stops where the nth root of n is less, or nth root of x is less than 2, as then pi of x is equal to 0, because we know that pi of 2 is 0, and pi of x can't be negative because you can't have a negative number of primes, i.e. pi of 100 has 7 terms, because the 8th root of 100 is less than 2. Brilliant. We can move on to the next slide. And we're getting back to the stuff that I was talking about before I forgot that you are still seeing the visualizer. And hopefully you're still not seeing the visualizer. I'm just going to check. Nope, you're fine. Right. And Riemann hypothesis. We can review our pi of x using or rewrite using our new function. So we have a pi of x, and we've got j of x minus j of root x minus the third j cube root minus the fifth j fifth root. This pi of x is the same thing as this generalized sum at the bottom. Basically, you've got a mu of n, and mu is 1 if n is square free with an even number of prime factors, 0 if n is not square free, and negative 1 if n is square free with an odd number of prime factors. And you just plug in your numbers, check out what mu n is, and off you go. And you get some pi of x. Right, brilliant. So now you can take logarithm of the Euler sum formula, which you had earlier. Because Euler sum formula is just a load of Euler product sum formula. And because it's products, basically log turns it into a sum. So now we have some sums, and we also have some, basically we can turn these logs into Taylor polynomials. And this is where I got to last time, when I realized that I wasn't showing you what I was supposed to be showing you. So if we have an f of x and we want to find a Taylor polynomial, we've got an f of x here, and we want to approximate f of x to some degree. We can say that f of x is equal to f of naught plus f prime of naught, x to the n, or x to the 1 over 1 factorial, plus f double prime of naught of x squared over 2 factorial, and so on. That's just how we define it. As a Maclaurin series, not really a Taylor series, but we're not using Taylor series. We're using Maclaurin because we're basing everything at 0, because we want the real part of a half, which is valid for this expansion. So it's a bit like binomial, but a bit more odd. You get this mess. There's a mess in front of you, but don't worry, we're just going to consider one of those terms. So let's take half times 1 over 3 to the 2s. That's equal to a half times s times the integral from 3 squared to infinity of x minus s minus 1 dx. And we can write this out in integral form by Taylor's theorem, which is what Maclaurin's theorem is a non-generalization of, or specific case of, and then do that for every term. And oh, why have we got 3 squared? That shouldn't be 3 squared, should it? That'd be 2. Should be 2. I've confused all the numbers, but yeah, you can then sum them together and use linearity of the integral, blah blah blah, sub in j of x, and you get that the line of the zeta function is equal to the integral from 0 to infinity of the prime counting function j of x, which is a normalized prime counting function, times x to negative s negative 1 dx. And that is why the Riemann zeta function is to do with primes. One last slide before I shall open up to questions. I find this really fun. It's not exactly primes, but we can use Fermat's last theorem to prove that there are infinitely primes. Some people use the expression a chainsaw to cheese. This is very much chainsaw to cheese, but Fermat's last theorem implies infinity of primes, and that's amazing. And that is all from me. Yes, thank you very much. That is all. I shall now open up to questions. And yes, well, I'm on Twitter at leftjames_a. On YouTube, not much on there at the moment, but also got a website, leftjames_a.co.uk.